Okay, hey, welcome back. So, finally, 15.8, the last section in the vector analysis chapter. Um, the story of Stokes' theorem again begins back with Green's theorem and the alternate forms for Green's theorem. So this is more of a direct translation than was the divergence theorem. If you remember the divergence theorem, we're kind of dealing with, we want to know alignment between the normal vector and the force field. Here is more about alignment between the tangent vector and the force field. So we can kind of begin with, so let's kind of at least introduce this with a section titled Stokes. We can begin with the original line integral. And then we have Green's theorem, of course. So double integral of these partials of the components of the vector field subtracted. And you could write this in a vector form then using the curl. Okay. So for us, back in the Green's theorem section, this would have been some curve in the plane, right? So what we want to do is just take it up one dimension and consider surfaces and things like that. Okay, so anyways, the alternate form of Green's theorem says that we could rewrite Green's theorem in vector form as the curl of f dotted with the vector, basically the 0, 0, 1 vector dA. Okay. All right, so if it's in the plane, then basically the normal vector is the k vector, the ijk, so 0, 0, 1. Okay, so hopefully that's obvious. So this is before, and this is the alternate form of Green's vector form. And now we will have Stokes, which is basically just the same thing, except rather than dealing with a curve in the plane, you can have a curve which is the boundary of some surface in space. And the thing that will change will be that vector that we're dotting it with, this thing right here. So it won't just be the k vector, the 1, 0, 0, 1. It won't just be that. It'll have to be some normal vector to the surface, which could be variable, right? So now with Stokes, it'll basically be the same concept. So you're going to be able to convert a curve integral, or a line integral rather, into double integral, surface integral of the curl of f, dotted now with whatever the heck the normal vector is for that surface. Okay. Okay, it's pretty, that's pretty much it. We have a physical interpretation of the curl coming, just like the divergence. And you think of divergence as kind of the flow out or the flow in. Curl is the flow around some normal vector. Okay, so at the end then we'll introduce that physical interpretation. I just want to go along the same route that the book goes, so it's not confusing if you've been reading the book. Okay, so first we want to verify Stokes' theorem. So we want to do an integral in two different ways and show you get the same answer. So again, I'll use kind of the same object I was using last time, elliptic paraboloid type object. So section 2, verifying Stokes. So just take a random example here. My force field, negative y plus z, comma x minus z, comma x minus y. And our surface is one of these elliptic paraboloids. Z equals 9 minus x squared minus y squared, and we want z to be greater than or equal to 0. So the picture of that thing is going to be like one of these objects. Okay. And the projection, the xy plane, is just a circle with radius 9. So if we're doing a double integral, we'll need to be able to integrate over this region. This is 9. Probably want to go to polar coordinates. Anyways, for the line integral, what we want to do is integrate around this boundary. Okay, and it just turns out that that boundary will be in the xy plane. Okay, so anyways, that curve, let's parameterize that thing. The curve will be some r of, let's say, theta, and we could say that is, how do we want to do that? Well, there's one issue with these boundaries. You have to go counterclockwise. You need it to be oriented in that way. So counterclockwise is this direction. So I'm going to be kind of careful that I get it in the right direction. And I'm going to use just 3 cosine theta, 3 sine theta, and then 0. Okay, so for my integral, I need the derivative of that thing, of course. So that would be negative 3 sine theta, comma 3 cosine theta, comma 0. And then I can do this line integral. So that will be the integral from 0 to 2 pi of, where's my f? It's up there somewhere. I'm going to have to reparameterize that in terms of theta. So I use my r of theta formula and kind of substitute that into the components here. All right. So I'll have negative y is negative 3 sine theta plus z. Z is 0, thankfully. And then my x apparently is 3 cosine theta minus 0, and then x minus y, unfortunately, 3 cosine theta minus 3 sine theta. Okay, and then I need to dot that with r prime. So dotted with then negative 3 sine theta, comma 3 cosine theta, comma 0, thankfully, d theta, and here we go. So this will be the integral of 9, well, that's going to work nice, right? 9 sine squared plus 9 cosine squared plus 0 d theta. Sine squared plus cosine squared is 1, so I'll just have the integral of d theta, factor out the 9. That will be 9 theta from 0 to 2 pi, and of course that will just be 18 pi. Okay, so there's the line integral, and you know, sometimes doing that integral can be quite annoying, so it may be easier just to use Stokes' theorem and do this as a double integral. Okay, I think in this case it's actually just a little more complicated, but anyways, let's go at it, right? So what do we need for this double integral? We need the curl of f, and then we need to dot that with the normal vector ds. So the curl of f, first off, so I need I, j, k. You probably forgotten, but we introduced curl back in 15.1. Partial with respect to x, partial with respect to y, partial with respect to z. And then we have, what the heck was our, jeez, I have to rewrite that down here somehow. Maybe if I zoom out, I'll be able to see it. Okay. So f is negative y plus z, x minus z, and then x minus y. Might as well rewrite the surface as well. C equals 9 minus x squared minus y squared, where z is greater than or equal to 0. Okay, great. So plugging in these components, negative y plus z, x minus z, x minus y is going to give me, cover up the first column. With respect to y, it would be negative 1 minus negative 1. And then the next component, negative, whatever, cover up the second column. It would be 1 minus 0. And then the third component, cover up the third column. It would be 1 minus -1. Okay, so our vector for the curl is going to be 0, -1. Oops, did I screw up that component, the second one? So it would be 1. Did I put them in the wrong place? It's -y plus z, Dave. All right, sorry. So I screwed that up. So this guy would be 1, and I think that will work then. Yeah. So the first component is 0, and then 0, and then 2. Okay, we're good. All right, so double integral over basically the projection of that onto the xy plane, projection of the surface onto the xy plane. We're integrating over that region. You probably want to go to polar coordinates to pull this off. Anyways, the curl, we have 0, 0, 2, dotted with the normal vector. So for the normal vector, you need to convert this surface here into g, x, y, z format. So you have z plus x squared plus y squared minus 9 equals 0. So you're getting basically the gradient, which will be, you know, the numerator of the normal vector, and then the denominator will cut into the ds, leaving you with a dA. So this part will be 2x comma 2y comma 1, and then our dA. Let's rewrite that then. 0, 0, it's just 2. Ain't that nice? dA. So let's go to the polar coordinates. In that case, r will be over here on the right. The equation of that circle is 3, and we're going to go from 0 to 2 pi. Okay, so polar coordinates have the integral from 0 to 3, and then 0 to 2 pi of 2r dr d theta, and then I have the integral 2r squared over 2, so r squared from 0 to 3 d theta, and then I have basically a 9 in there, d theta, and then 9 times theta from 0 to 2 pi, which is 18 pi, which is exactly what we got doing the other way by just integrating around the surface. Okay. So, you know, with Green's theorem, it was basically, you could literally find the area of a region by just integrating the curve that was the boundary of that region. Now we're finding we can kind of pull the same trick if we have a surface. So you can either integrate around the boundary of the surface or integrate over the surface, and you'll get the same answer. Okay. Okay, so let's, you know, in general, you're going to be doing the double integral in the homework problems. You know, most of the homework problems turn out to be 0 if you're looking at my answers. 1, 2, 3, 4 out of, you got a 50-50 chance if you answer 0. Okay. All right, so anyways, let's try number 6. 6 looks intimidating. For a lot of these integrals, I did convert the polar. Like almost every one of them I did. Let me look through. So number 1 I did not convert the polar. But number 2 I did not convert the polar. Number 3, I converted the polar. And it was not fun. Number 4, I don't see it anywhere. Must have been really easy. No, number 4, I converted the polar. And it was nasty. Number 5, I converted the polar. Number 6, I converted the polar. Number 7, I converted the polar. Number 8, I somehow got clever and figured it out. Okay, so yeah, some of these are nasty. Let me see if I can find one that was nasty so we can do it. Is number 3 nasty? think number 3 was kind of nasty. But some of these look really, really kind of crazy. It's number 4. I wonder what problem this was. Maybe it was number 6. Just one second, almost there. Number 7's annoying because you have to remind yourselves how to graph polar and polar coordinates. Maybe that was number 6. It was kind of nasty. Well, I'll do more than one. Let's try number, sorry. Well, let's try number 3, right? So let me take a half hour just to figure out. I'm going to do the one that I thought I was going to do in the first one. Okay, so number 3, our force field is 4xz, comma y, comma 4xy. The surface is going to be basically the same sort of surface we were dealing with, an elliptic paraboloid, squared, and then z is greater than or equal to 0. Seems like all of them are spheres or elliptic paraboloids. Okay, so I need to get the curl. Is usually the first kind of hurdle to deal with. And of course, I'm doing my double integral. Okay, so I have the curl of f dotted with n ds. All right, so curl of f I j k partial with respect to x, partial with respect to y, partial with respect to z. Then we have 4xz, y, 4xy. Cover up the first column. You get 4x minus 0. The second column, cover that up. You get 4y minus 4x. Cover up the third column. You get 0 minus 0. Well, that's nice of them. So this will turn out to be 4x, then 4x minus 4y, and then 0. Going to then our double integral. We have that vector 4x minus 4y, 0. Do you need to dot it with basically, well, we need to convert this thing first, okay, into some function of g of x, y, z. So that will be z plus x squared plus y squared minus 64 equals 0. So our gradient of that, 2x, 2y, 1. And then dA. Let's see what we get. Got to the 8x squared plus 8xy minus 8y squared dA. I'm going to go to polar coordinates. If not, you're going to be dealing with a lot of square roots, which you could deal with, but I just do not like square root functions at this point in life. So I'm going to factor out the 8, and then converting the polar, you can't quite get rid of the x squared plus y squared and just put an r squared. That ain't going to work, right? Because you got x squared minus y squared. You need x squared plus y squared. So sorry to ruin your day. I'm also going to have to distribute an r into the expression, so it'll be an r cubed eventually. So I'll have r cubed, x squared is r squared cosine squared. So r cubed cosine squared theta plus 8r cubed cosine theta sine theta, and I already factored out the 8, sorry, minus r cubed sine squared theta, d theta, dr d theta, dr d theta. Okay, butchered the r there. Theta. Okay, so I have 8. I want to integrate that with respect to r. That's not too difficult. In each case, you'll have r to the 4th over 4, so you can factor out a 1/4. You'll end up with a 2 and leading. So I have the double integral of, basically, it's just, can we just factor out that r to the 4th, and then evaluate it? So r to the 4th over 4. And then we have cosine squared theta plus cosine theta sine theta minus sine squared theta, evaluate this from 0 to would be 8 because the radius is 60. The radius is, well, the original function would be x squared plus y squared is 64 in the xy plane. So you'd have 8 up top and then d theta. So putting in there 8 to the 4th, well actually, yeah, it's 8 to the 4th over 4, and then there's a times 2. So it seems like, what did I screw up? It seems like I screwed something up. It's just 8 to the 4. Where did I get a 3? Somehow I got an 8/3 out of this. Maybe my answer. Maybe I screwed up my answer there. Anyways, looks like I'm getting 8 to the 4th all over. And my answer on my notes is wrong. So great. 8 to the 4th. The one problem I picked has screwed it up somehow. So anyways, 8 to the 4th over 2. And then integrating all this jazz. So that will be cosine squared. You got to use reduction formula. So 1/2 plus cosine 2 theta all over 2 plus cosine theta sine theta minus, what do we have then? 1/2 minus cosine 2 theta over 2 with another reduction formula there, d theta. And then that's going to give me 8 to the 4th over 2. And we have the integral of, so the 1/2s cancel, and you'll end up with 2 cosine 2 theta over 2. So just cosine 2 theta plus cosine theta sine theta d theta. And then you could just integrate that straight across. Cosine 2 theta, its integral is sine 2 theta all over 2. And then for this, you could just do a u sub on sine, and then du will be cosine theta d theta. So you're going to get u squared over 2. Back subbing, it will be sine squared theta all over 2. And then we want to evaluate that from 0 to 2 pi. But in both cases, that's just going to be 0. When you plug this 2 pi into here and here, you'll have sine of 4 pi, which is 0, and then sine of 2 pi squared, which is also 0. And then when you plug these in, you're going to get 0 and 0, and then 8 to the 4th over 2 times 0 is 0, which is why I sort of got away with making a mistake when I did the problem, but I still ended up getting the answer, which is 0. Okay. All right, so good stuff. Let's look at, I guess, number 6. We'll make that one the video quiz. So we have the force field, and this one, is definitely, I'm going to have a severe panic attack kind of problem. Negative ln square root of, not to make fun of panic attacks, I've actually had panic attacks, they're not a lot of fun. I know I've had the drive home from Cleveland having panic attacks back before I knew what panic attacks were. And that was extremely dangerous. So if you need to, always go see a counselor, especially in college, because you'll be super stressed, and if you have any issues, they will come to the surface, any physical issues, any emotional issues. So definitely take advantage of the counselors. But anyways, always just... Okay, so z equals 6 minus 2x minus 3y, and this time we're integrating over the region r equals 2 sine of 2 theta. Okay, so the fact that we're integrating over a polar region kind of tells you we're probably going to be doing a polar integral. First, let's go ahead and get the curl business out of the way, and then we'll worry about the region that we're integrating over. So the curl of this f, which looks like some craziness, but it turns out to reduce kind of nicely. Okay, So partial with respect to x, partial with respect to y, partial with respect to z. You get negative ln square root of x squared plus y squared, and then arc tan of x over y, and then 1. So cover the first column, partial y with respect to that's 0. Both of those are going to be 0, comma negative, parentheses. Cover the second column, partial of 1 with respect to x is 0, partial of that natural log thing with respect to z is also 0. So you would get 0 minus 0. I tried to put a comma in there to confuse you. Then the third component, cover up the third column, and that's where the fun begins, right? So you get 1 all over 1 plus x over y squared times the derivative of x over y with respect to x, which will be 1 over y, and then minus a negative, so it'll become plus. Let's rewrite this thing as 1/2 ln of x squared plus y squared. That way it's a little easier to deal with. So we'll have a plus 1/2, 1 all over x squared plus y squared times the derivative of y, of x squared plus y squared with respect to y. So I get 2y. Okay, so this will be 0, 0. I want to get rid of this complex fraction and this expression. So I'm going to cheat a little and I'll multiply it by another factor of y, top and bottom. So I end up multiplying the bottom by y squared and the top by y. Okay. So in the numerator I'll have y, and the denominator you'll have y squared plus x squared, right? Because the y squared will cancel in that second term. And then plus just y over x squared plus y squared, and you see, oh, that's not a big deal. I don't know why I was upset about this. It's just 2y all over y squared plus x squared. Okay, great. Then what do I need to do? I need to figure out the surface, the region I'm integrating. So it's a plane over this region. Okay, so I need to get that region for my double integral. So what the heck is that thing? R equals 2 sine of 2 theta. Well, that's one of our Rose curves, right? So if you don't remember how to pull these off, I'm going to first graph it in the r theta plane, or rather theta r plane, even though the coordinates are always given as r theta. So first we have the amplitude is 2. Secondly then, for the period, we have wedging 2 theta in between 0 and 2 pi. The period will go from 0 to pi. And then thirdly, for the tick marks, divide that by 4. So pi over 4s. So in the theta r plane, well, I guess I was right. No, it's the theta r plane. Okay, so 1, 2, 3, 4. So pi over 4, 2 pi over 4, 3 pi over 4, and then 4 pi over 4 is right there. Amplitude is 2, and then it will repeat itself. But we only need, if you were looking carefully, I think we only need the first octant region. Yeah, so it says over the first octant. Okay, so you only kind of need the first quadrant then I'm integrating over. So to graph this thing, I go to the xy plane, put some helper circles in there, and then draw some angular lines at pi over 4. So at pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, etc. Right? So the first part of the curve goes from 0 to 2, and then we'll be at pi over 4, right? So it's going to increase from 0 to 2 at pi over 4. And then from pi over 4 to pi over 2, it decreases back to 0. Okay, and that's really the only part of the flower we need. That's what we're integrating over. So we have one full flower petal going from 0 to pi over 2. It's really all the information we need from that. Right, so I'm going to take my double integral now. It's going to be a polar integral. So I'm integrating from 0 to pi over 2, and the r value is going from 0 to 2 sine 2 theta. I hope that's not too scary. And then I have the curl of f which we found to be 0, 0, and then 2y all over y squared plus x squared. So that's going to be 2r sine theta. X squared plus y squared is just r squared, right? And then dotted with, well, I guess we can't really convert to polar just plain old yet, right? Because I need to get this normal vector. So maybe I'm getting ahead of myself a little bit. So let me chill out on converting the polar just yet. So right now it's just y all over x, I apologize, plus y squared. And then dotted with this normal vector from this g function that we have yet to figure out. G of x, y, z is going to be z plus 2x plus 3y minus 6 equals 0. So I need the gradient of that thing for my normal vector. Let me zoom out a little bit so I can see it. So dotted with the gradient 2, 3, and then just plain old 1, I guess so, dA. And then I could probably convert if I want to. So it'd be 0 plus y over x squared plus y squared, which is going to be r sine theta all over r squared. And then we have an r dr d theta. We're going from 0 to 2 sine 2 theta, and then from 0 to pi over 2. And then we should be home free, right? So there's a nice little cancellation for us. R times r is r squared. All over r squared will just leave us with sine theta, dr d theta. And then we have double integral integrating with respect to r. So let's get rid of one of the integral symbols. I'll have r sine theta evaluated from 0 to 2 sine 2 theta d theta. Substitute in that expression for r. We'll end up with the integral of 2 sine 2 theta sine theta d theta. I'm going to use a trig identity to rewrite that as 2 cosine theta sine theta. So I'll end up with 4 times the integral of cosine theta sine squared theta d theta. And then you could do a u sub for sine. So u equals sine theta. And of course the differential part will just be cosine theta sine theta, or cosine theta d theta. And then you'll have 4 times the integral of u squared du. So you'll have 4 times u cubed all over 3 evaluated from 0. Well, we have to back sub first, right? So I keep getting ahead of myself. So this will be 4/3 times sine cube theta evaluated from 0 to pi over 2. So usually it's just 0, but because we're going to pi over 2, it's going to just end up being 4/3, right? So sine of pi over 2 is 1, 1 cubed is 1, sine of 0 is 0, so the second half of the integral just goes away. And no, oh no, no, no. I'm thinking I somehow lost a factor of 2 somewhere. Oh, gee willikers. How did I manage that? It was back here somewhere. Is the original, did I get the vector field wrong? Is that what happened? Yeah, no. Oh yeah, my derivative's wrong. I tried to do it. I'm such an idiot. It has a 2 on it. So yeah, so this would be 2, this would be 2, this would be 2, this would be 2, this would be with a 2 in front, so this would be 8, this would be 8. Sorry. I mean, this whole last chapter is pretty rough. with respect to doing all these integrals. At least for me, it's always rough. I don't know how it is for you guys. If it was rough for me, I'm expecting it was probably rough for you too. Anyways, that will be the last video quiz for Calc 3. Congratulations. Thank you for putting up with me this semester. I appreciate all of you watching the videos and doing the video quizzes. And I wish everyone best of luck in the future. And oh, I didn't talk about the physical interpretation of curl. I apologize. We got to do that as well. Okay. So what the heck is this curl thing? It's basically if you have a surface and you want to know kind of what the curl is at this point on the surface, basically you think of it as a rotation about some normal vector. Okay. So it's always with respect to a normal vector. So you say that curl dot n. And basically, the physical interpretation will work similarly to the physical interpretation of divergence. We'll kind of define a small itsy bitsy circle on the surface, give it a name, and we could set it up as equals the curl is equal to some integral, and then factor out the curl part because it's going to be constant if the circle is small enough, and then take a limit as eventually take a limit as the radius of that circle goes to 0. So anyways, this physical interpretation section 3 now. Just when you thought I was done. Interpretation, hopefully I spelled that right, of curl. Makes you feel better. I learned how to write before I went to, my dad taught me everything about writing and everything before when I was like really young, so I apologize. His first language wasn't English, so he taught me a lot of the he didn't know how to spell, so it's funneled into me. I'm not an idiot, I swear, but there it is. Okay, so anyways, let's worry about this physical interpretation now. So our line integral, what it is kind of an alignment between a force and a tangent vector, right? And you could think of this, if C is a closed curve like this, you could think of this as the alignment between the tangent vector and whatever the heck the force field vector is. So it's a tangent, and you can imagine if that force field was always kind of going in the same direction as the tangent, you're going to get kind of a resulting circulation around this curve. Okay, so you kind of think of it as a force field is kind of pushing in the same direction as motion, so it's going to go faster and faster. Okay, so that's kind of how you want to think of this thing. It's right now it's if your curve is closed, it's a circulation issue around C, right? Okay, so what we want to do now here in with this double integral, in order to get the interpretation of curl, is to take a surface and consider a small curve on the surface, in particular kind of a circle on the surface, and there'll be a normal vector associated with that small circle, and we are going to be kind of figuring out the circulation around that little circle. So this little circle, instead of what did we call it last time? We call it S sub alpha. We call it the same thing this time apparently. So this little circle here, I guess this curve C, I'll say C is S sub alpha. Okay. And then the circulation around this curve, because of Stokes' theorem, we can now rewrite this as the double integral about that circle, or over that circle rather, of the curl of f dotted with the normal vector there, ds. And then supposing that the force field is continuous, if this s sub alpha is small enough, we could factor this part out as a constant, right? So we could say this is the curl, this whole part, even the dot product part, curl of f, serious trouble writing, curl of f dotted with n, and then we can solve for that, right? So times the double integral of this s sub alpha, which will be the surface area integral. Okay, because it's a disk, then and it's small enough, we could say that this is just the area of a circle, so pi alpha squared. So this will be the curl, and there should be some approximations here. So we're supposing the curl of f is constant. The curl of f dotted with n, and then times pi alpha squared, and then you could solve for, you know, your curl dot n. That will equal, you know, and ultimately taking a limit, the limit as alpha goes to 0 for curl at a point of 1 all over pi alpha squared of this curve integral. And what that represents is the rotation of the vector field at a point about a normal vector. Okay, so this would be the rotation of f about n. Okay, so long story short, the divergence tells us about stuff flowing in and out. Curl tells us about rotation around a point. Okay, so that pretty much does it for me. I'm floored about this material. It's really interesting. I think over my break, I'm going to sort of see go look for some applications, ask one of my engineering friends if he could find something for me. Probably, I'm thinking it's fluid dynamics, right? Because you have rotation. I remember being in just one small statement, and I promise I'll shut up. I remember being at Cleveland State in the library on the fourth floor, and I used to sit there and just study, look through their books. They have a massive library there, back when libraries were something. I go there and I found a book that was all about the liquid dynamics of coffee in a coffee cup. Somebody had done his entire thesis on the flow of coffee in a coffee cup. It was like it looked like a pamphlet, really, but it was really cool. It's in the Cleveland State Library if you ever get a chance to go there and look it up. I don't know if it's there anymore, though. So they're trying to kill off the libraries. Well, learning's bad, you know. Okay, I'll shut up. Thank you for watching. I appreciate you watching. If you stuck it out to the end, you know, +1. You can email me. Where's my +1? You know, I want 1 extra credit for watching all these dumb videos. Okay, no, they're not dumb. All right, so thank you for watching. I wish you the best in the future. I sometimes teach differential equations as well, so maybe you could take that with me if you want to. But other than that, I guess I'll see you. Good luck, and thank you for watching, and okay, bye.